otherwise, today let's continue our discussion on quantization. So what's the context? This is when we have a finitely many bits to represent every number, right? So we need to perform rounding. 要做一些四舍五入这样的步骤。We need to perform rounding, by ignoring the fractional part of every number. Suppose your quantization step is regarded as integers. So the idea here is that so from continuous time we can go to discrete time by sampling the signal, and the result is one number each time. Every sample is one number, and that number should be quantized. Should be quantized. So the result is denoted as x hat right here, which differs from x itself. And there's one detail that I didn't mention clearly last time, so let me try to explain. Here we have this range right here and that range over there, right? So this is an emphasis that we will need to decide what's the full scale. You cannot encode like an infinitely large signal, right? So one way or the other, you need to decide beforehand that what's your full scale, plus or minus xm, okay? That's the full scale. Anything that's beyond this range, outside this range, will be clipped. Now, there's nothing we allow nothing to be outside this range. So anything that is originally out, I'm sorry, we need to clip it to positive or negative of the full scale, xm. That clear? Yeah. So that we call this full scale level. Full scale level. But what's going on here? Right here is just some normalization. Okay. So sometimes it's more convenient to think about to regard the largest scale as equivalent to +1, and negative of that is equivalent to next one, equivalent to -1. So this is just normalization, Okay. And this is particularly useful when you, now in this homework, there's a part which requires you to run a piece of MATLAB code, right? So in MATLAB, for example, when you load an audio file, speech or music, audio file, right? When you load an audio file and you can just check the content, what's inside. There will be samples stored in an array, array. There will be samples, and their values are all between minus and +1. So for real, like in MATLAB, there is such kind of normalization by default. When you load a piece of audio file, then it converts it to this range, normalized, between -1 and +1. Okay, so that's in practice. Sometimes you check the content of the file, you find all the values between -1 and +1. Right? We'll take a look. So but that's the idea. Okay, so we really need to encode our numbers by some kind of quantizer. So what does the quantizer do? Last time we showed this plot, this nice little plot with a kind of this is essentially an I/O function, input-output relation. Okay, an I/O function. And in this I/O function, in this particular example, we have 3 bits. We are using 3 bits to encode every number. And as we all know that if you have 3 bits, then you can only encode 8 different levels. 3 bits equivalent to 8 different levels. 4 bits, 16 different levels. Okay, just for easier to show this more easily, we just use an example of having 3 bits to encode every number. So we have 1, 2, 3, 4, 5, 6, 7, 8. Come on, baby, say you love me. sorry, 有一首老歌啊 5, 6, 7, 8 非常老的歌 1980年代啊 3 bits, 8 different levels. With the middle level is 0. 0 is very important, right? So we also briefly talked about the different ways to assign your string to level. to each level. So in 2's complement code, 0 is 0, but -1 is encoded as 111. Yeah. All right. 8 different levels for 3-bit representation. So far, so good? Yeah. So this is I/O curve. Yeah. So if we just write our input as any argument x, and the output of quantization is denoted as q of x, which equals to x or x hat. Okay. So just you see that in general there will be a difference between x and q of x. Before and after quantization, there will be an error. There will be an approximation error. So let's skip this slide. So last time near the end, I just emphasized that this is an important concept. Okay, important concept. So take a look. So here I was talking about quantizer being a function. So there will be input, there will be output. Output is denoted as q of input, right? Yeah. But somehow it's more convenient to think of this system, to model this system as if we are introducing an approximation error. Very simple concept. Now, what is approximation error? Approximation error is just defined as the output subtract the difference between the output and input. Okay, that's the approximation error. E denotes for error. Okay, and this is an important trick. Okay, very important and convenient trick. So then we can talk about statistics properties of the approximation error. Statistics, 统计上的一些的性质statistical properties of the approximation error. So there are a few questions. First of all, so let's take a look at one example. This is our signal in discrete time already, but not yet quantized. Not quantized yet. Okay, still with continuous value. Yeah. But then after quantization, it is approximated by any one. All the samples are approximated by one of the 8 levels, right? This is an example of having 3 bits representation with 8 levels, 1, 2, 3, 4, 5 to 8, right? So then in the next slide, we also plot the approximation error. So this is the approximation. That's the result. That's the output. Okay. So just as kind of brain teasing, 脑筋转一下弯, a brain teasing exercise. If you that means when we sum up this one and this one, it equals to the original signal before quantization. That's the idea. Okay, because error is defined as this guy subtracted by the input. Okay, but you know the idea. So that's the approximation error when we have only 3 bits for quantization. Okay. And similarly, this is the result when we have 8 bits for each number. So immediately you notice that the approximation error now is much smaller when we have 8 bits compared to when we have 3 bits, right? 8 bits, of course, you have a finer resolution. 解析度比较高嘛. You have a finer resolution, you have a smaller approximation error. So that makes a lot of sense. And secondly, beyond that, I was asking one question. I asked you to kind of just by inspection, 用看哦, by inspection, by expecting these 2 figures, which one do you think is more random, right? So I raised this question for you to, you can have your opinion, okay? Simply by looking, which one looks more random? To my eyes, this one looks more random, and there are reasons. For example, like here, things don't look random, right? This is when the signal is clipped. So this doesn't look random, right? But then when we talk about the errors being random, we need to be more precise about our terminology. 我们要用词要再更精确一些. We need to be more precise about our terminologies. What do we mean random? What do you mean random? So there are at least 2 different notions I can share with you. One is the distribution. Okay, so approximation error, you just create this kind of plot, plot using bars. So you see that this is the example of having 16 bits versus 8 bits. Okay. So, and the way we read it, this is the range of error. Okay. So as you see, having 8 bits, when we have 8 bits, the range is somewhere between minus and plus or minus 4 times 10 to the minus third. No, 0.004. 0.004. Okay, that's a range. Okay, in between. The error could be anywhere in between. Yeah. Now, when we have more, like 8 more bits, of course, the range of the error is going to be further reduced. Now it's even smaller in between plus or minus, let's say 1.5 times 10 to the minus fifth. Okay, 1.5乘以10的负5次方 So that makes a lot of sense. And now you notice that, so this is one example. You take a signal, you quantize it, and then just count how many times you have an error that's exactly in this range. This is histogram. Yeah, I was trying to recall what's the term. 长条图了 histogram. Yeah. This is just nothing but a histogram. Yeah. Yeah. So now we can just again by inspection and decide which one is more uniformly distributed, right? Uniform distribution. Okay. Uniform distribution. So apparently this is more uniformly distributed than that. Okay. So that gives us some kind of insight. Is there some kind of insight right here? Does that mean that when we have more samples, the more uniform? The more samples we have, no, not sample, the more bits we have, the more uniform the distribution will look like. Okay, so there's an insight. I think the answer is yes. Okay, but this is just one example from the textbook. So any idea why this one doesn't look as uniform as on the top? Any comment? Well, why do we see this? What's the reason? What's the reason? Okay. Check the textbook. So anyway, so yeah. So that's an example. So there's at least one notion of randomness. We can consider the distribution. And distribution is important because if the distribution really is uniform, then we can easily calculate the noise power. And that's great. That's a great idea, a great thing to do. So here is the way we model the distribution. Suppose that we now just can think of our approximation error as a random variable. For each sample, E of n. So we can think of E of n as a random variable which obeys certain kind of probability density distribution, a PDF, probability density function. Okay, yeah. And in this case, the probability density function is denoted as p, lowercase p, 小写的 p, small p, with subscript en, emphasizing that that's a random variable. Okay. Of which we consider is distribution, and that distribution is a function. And this E here is just a dummy variable, doesn't really matter. You can say it's X, yeah, doesn't really matter. But the important thing is that now if we believe that the approximation error is uniformly distributed, then this is the density function, okay? So for all of us that have taken probability, let's recall, this is a uniform distribution, continuously valued. Okay, continuous value, uniform distribution, and the distribution has a zero mean. The mean is 0 because the middle is 0. Okay, the mean of approximation error is 0, and the distribution is anywhere in between half, plus or minus from minus to plus 1/2 of the quantization step size. 1/2 of delta. Delta is here. Full level multiplied by 2 to the minus b. Okay. So that is a quantization step size, if you recall. The level, how large is our in between two adjacent levels? 两个相邻的集距啊 the quantization side, quantization step size 啊 So now that's a probability density function, which in the sense that if we take the integral, right? Take the integral of any probability density function, then it needs to equal to 1, right? It has a the area below the density function needs to be 1. Okay, so please just remind yourself that's probability. So this is a random variable, so we can consider its mean. We can also consider its variance, right? So apparently the mean is 0. And variance in this case will be, let's say, the variance of E of n is an expected value. 会是一个期望值啊。Variance is an expected value of what? Of E of n as a random variable minus its mean. Square, and we take the expected value. Okay? But so seriously, so what is the expected value? How do we calculate the expected value of any random variable? Do you remember that? Yeah, for those of us that have taken probability. Have you taken probability? Some of you must have taken it, okay? It's the PDF, right? And what else? Yeah, so the range of integral is the what? The sample space, which is in between -2, minus 1/2 of delta to from minus of that to plus of that dx. Okay, and so you'll be able to show that the result, now I memorize, is pretty straightforward. Delta squared divided by 12. There's a factor of 12, right? Where delta is our quantization step size. Okay, so it's a rather straightforward derivation, which I'm not going to show right here. Just in case you're interested, please verify by yourself. So we could that's the power of noise. Okay, the expected value of the quantization noise square, given that it's zero mean. We know that mu is 0. Okay, mu is 0. So already we have a statistical model for quantization noise. Okay, for quantization error, for the error that's introduced by quantization. And it's random in the sense that it's uniformly distributed. So we can talk about, for each sample, what's the expected value, what's the variance of this random variable. Okay. Yeah, that's one notion. You can really calculate the power in the sense that it's an expected value of a square of that random variable. Okay, square of the approximation error. So this is a way to model the noise. Okay, sample by sample. Every sample is a random variable. We are not sure, but just statistically, the average of the noise square should be equal to delta squared divided by 12. Okay, delta squared divided by 12. So far so good? Yeah. Assuming that the error is uniformly distributed. Yeah. And now, so to summarize, this plot, when we look at it, it assumes that quantization error is uniformly distributed. At least this would be a good simplification. Okay, but further, we often also assume a few additional points. The first point, error is stationary. As a random variable, error is stationary. Its statistical properties does not change from one sample to the next. I mean, every sample is going to be different. It's random. Yeah. It's like tossing a coin or 掷骰子 or yeah. It's random, but anyway, the distribution itself is stationary. Every sample has the same distribution, okay? Stationarity. That's the first assumption. And the second assumption is also interesting. Error is often assumed uncorrelated with the signal. Uncorrelated, okay? What do we mean? So that means when we have a signal and we have the error, uncorrelated means the correlation coefficient is 0 in that sense, okay? So now we need to remember to check what's the definition of correlation coefficient, okay? Or no, the covariance, okay? Yeah. So we can then consider the expected value of E of n times x of n minus the mean of x. Okay, let me use this notation. So that's a covariance, knowing that the mean of E of n is 0. So that's a covariance between the approximation error and the signal that we begin with. Okay, the covariance, so we often make this assumption that the two of them are uncorrelated, meaning that this expected value is what? Is 0. Okay? Meaning that you may increase the signal, decrease the signal, but the error, approximation error, is not positively or negatively correlated with the value of your signal. Okay? That's an assumption. Okay? Like there is a 0 correlation between the two of them. Okay? That's an additional assumption. So already you're seeing that we can have more and more further discussions. Okay? So far so good? Any comment? Do you believe it? Your signal, you have a piece of audio signal or a piece of, I don't know, ECG or brainwave. Yeah? Okay, yeah. And quantize it with 8 bits, and you just calculate the estimate, just evaluate all the approximation errors sample by sample, and we assume that often this assumption is quite valid. Okay, the signal is uncorrelated with 0. The quantization error will be uncorrelated with your signal in the sense that their covariance is 0. Okay. So that's the second point. And the last point I want to share with you is that error is also often considered white. 白杂讯啊, white. So what's the meaning of being white? When we talk about a random process, a random signal. Being white means that the spectrum of your signal is more or less flat. It has that notion. White. What is white? Because white is a color, right? So what color is white? Because it's wide band. It contains all the colors, right? All the colors in the rainbow. When you add them, is the white color, white light. Yeah, not here because this is fake white. 日光灯了, yeah, but like sunlight is white because it's broad spectrum. Okay, so we borrow the terminology, 把这个想法又 borrow 过来啊. So for any statistical signal, so when we measure the spectrum, if the spectrum is kind of flat, or ideally if the spectrum is exactly flat, then we say that this random signal is a white signal. Okay, so the sufficient condition for a random signal to be white is when the samples are what? Independent. Independently distributed. Okay. Let me elaborate this. 我把它稍微再讲细一点. Let me elaborate on this point. So white, to summarize, white, this terminology white means flat spectrum. Like the white light, having all the colors with equal power density from red to violet, right? 红到紫色, from red to violet, broad spectrum, flat spectrum. That's when we say white. But then, what is the spectrum of a random signal? So that requires a bit of kind of more advanced knowledge. Okay, so here we need to consider the Fourier transform because spectrum is in the frequency domain, right? But how do you consider the spectrum of a random signal? So you need to consider Fourier transform of what we call the autocorrelation function, denoted Rx, if you will, of n. This could be DTFT. Okay, so this symbol denotes DTFT. DTFT of not directly, you apply DTFT not directly to your signal, but to its autocorrelation function. And so for white, so if the Fourier transform of this is a constant, let's say constant d, okay, a constant, then we say the spectrum really is flat, constant, right? No variation against frequency. The result should be a function. The result should be a function of omega, but if it's a constant, then let's say from 0 to 2 pi. If it's a constant d, then we say the signal x is white. Okay. So then we need to define then what is the definition of autocorrelation function. Autocorrelation function. Autocorrelation function of a random process is defined as the expected value of x of n no. Let me use m, okay? M. X of n, x. When you shift x by m and consider its correlation with itself at a later time. Okay, let me repeat this. You consider the correlation between x and itself at a later time. Of course, m can also be negative, and we're talking about an earlier time. Doesn't really matter. It's evenly symmetric. Okay, so just roughly speaking, for if x of n is 0 mean, if xn is itself is 0 mean for all n, then the autocorrelation function has this expression. It's an expected value of the correlation between the signal and itself at a later time. Okay, and you just increase the delay, decrease the delay. The result is going to depend on m. Okay, the result is going to depend on m, and this thing is called autocorrelation function. Okay, so there are a lot of twists already. So yeah, please follow me. Okay, so far so good? Yeah. So we're talking about error is also often assumed to be white. Then there is some background knowledge that we need to mention. We need to mention then what do we mean flat white? Oh, white means flat spectrum. What do we mean flat spectrum? What spectrum? The Fourier transform of what? oh, the Fourier transform of autocorrelation function. Then what is the definition of autocorrelation function? So there are a few steps before we can just precisely talk about what do we mean spectrum being white. Okay, because everything here is statistical. 所有东西都是统计的. Everything here is random, right? Okay, so now finally, the final step is simple. So then we ask the question, what kind of autocorrelation function will have a constant DTFT? Then we can ask this rather simple question. Which function in time domain has a flat spectrum? Which function has this property? Delta function, right? Yeah. So in other words, if this is constant, so if the Fourier transform is the Fourier transform of the autocorrelation function of x, which is DTFT, is a constant d, then there might be a factor of 2 pi, but you can apply inverse Fourier transform, right, to figure out the autocorrelation function. Seriously, this is a Fourier transform pair, right? So by inverse Fourier transform, so we know that Rxx of n should be 1 divided by 2 pi. Take the integral. This is the spectrum. What? E j omega and d omega, right? So for any n that's not equal to 1, the result is 0. So the result is d divided by 2 pi. No, just d. Or yeah, just d. Is d when n is 0 elsewhere. Okay? Yeah, so this becomes the result that is useful. Okay? When we say the spectrum is flat, then blah, 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 after a few steps of organizing our thoughts, we reach a conclusion. Here we have a conclusion. We conclude that when the spectrum is white, equivalently in the time domain, the autocorrelation function needs to be a delta function times the density d. Okay? Delta function. But then what does that mean? That means the signal is what? Uncorrelated to itself at any other sample, at any other time. Let me repeat that, okay? That means what? That's a correlation, right? By definition, autocorrelation is a correlation with itself, literally, autocorrelation, 自我的 correlation, right? Autocorrelation. So that means that the signal is going to be uncorrelated to itself when we introduce a time shift. When there's no time shift, of course, that's a variance. Okay, that's already the variance that we were talking about, delta squared divided by 12. D equals to delta squared divided by 12. But otherwise, when we shift our signal, it's going to be, by definition, white means zero correlation between your signal and itself at a later time. Okay, so for those of you that are eventually going to be interested, go into the communication field. Okay, often conveniently in communication we assume noise is like what? IID. IID. So learn this terminology. IID. So a related terminology is independent identically distributed. Okay? Independent identically distributed, or IID. So this is a stronger condition. Okay, when a random process is independently identically distributed, that means that implies stationarity. Identical distribution. Every sample has the same distribution as the next sample. Identical distribution. It doesn't change. Same distribution. And also, not only are they the same distribution, but also they are mutually independent. That's a rather strong condition, which guarantees white spectrum. which guarantees because independence implies what? Uncorrelated, right? Independence implies zero correlation. The converse is not true, okay? So I say that's a stronger condition that which you will encounter a lot in the field of our communication. Usually we assume the noise, conveniently we can assume the noise is IID, okay? Simplifies a lot of things. Right, so, okay, so this is probably the only class in the entire semester in which we talk about probability, okay? So this is just give you to give you an idea, give you a flavor, 一点点感觉, that when we talk about error, we need to consider them, we need to just precisely define their randomness. So yeah, so after a somewhat long discussion about the definition of whiteness of our approximation error as a statistical signal, let's take a look. All right, so now it's an example of quantizing some kind of a signal. Any signal that interests you. Take a recording and then apply different numbers of bits. Okay. So here in this plot, in this figure, we have 4 different cases with increasing number of bits. From 4 bits, 8 bits, this is 12 bits and 16 bits. Okay, in the textbook, the number of bits is denoted as B plus 1. Okay, so just be aware that this is 4 bits, 8, 12, and 16. Okay, that's one detail to mention. Make sure that we have the same idea right here. But now we can take a look. Yeah, so really these things can be computed, okay, and plotted. Okay, so from your signal, you just estimate the expected value. Okay, estimate your autocorrelation function and then perform Fourier transform. So that's how we plot it seriously. Okay, just these things can all be computed. 都可以计算的, they can all be computed. But now, just conceptually, let's take a look. It seems like when we have 3 bits, the quantization error spectrum, the power spectra, okay, the result is called the power spectra, by the way. Power spectra, this thing right here. The power spectra here, plotting from 0 to Nyquist, okay, so that's 1 pi, okay. Plotting between 0 frequency, DC frequency, and the Nyquist frequency, you see that with b equals to 3, it's not that flat, okay? If my student tell me, teacher, I obtain a white spectrum right here, I say, no, it doesn't look so white, right? It's just not so flat, right? 3 bits. 7 bits, it's getting better, right? No, I mean 8 bits, not 3, 4 bits, not really flat. 8 bits, getting better. 12 bits, more better. Yeah, better and better. And this is the best among 4. The most flattened spectrum right here at the bottom. As well as now you can also notice that here, what's the unit right here? dB. Okay, dB. So this figure tells us a lot of things. First of all, the more it seems that apparently, it seems that when we increase the number of bits for our encoder, for our quantization, then we can flatten the spectrum of our approximation error. Okay, that implies that really the autocorrelation function is almost delta function. Okay, every sample's approximation error is going to be uncorrelated with the next. Okay, so that's the implication, or that implies. That's what it implies. And secondly, look at here. The unit is dB. Okay, flat spectrum, but the unit here is not linear unit. It's dB, log unit. Okay, log unit. So what can you say? What can you say? So here, let's compare these two. This one is like, in this example, it's near 100. okay, minus 100 dB. Whereas here is close to what? Can anybody give me a number? This is like minus 77, right? 负77 versus minus 101, okay, right? What's the difference? What's the difference? The difference is 24, right? 24 dB. Yeah. So there's a rule of 6 dB per bit. Okay, that's something that is quite useful, quite handy to remember. Okay, when you talk about quantization noise power, okay, remember that when we introduce, roughly speaking, when we introduce one extra bit, that that suppresses the noise power by 6 dB. 1 bit, 6 dB per 1 bit. Okay, so same thing here from 7 to 11. This distance is also about 6 dB per bit. And when we increase, that means when we increase by 4 bits, we expect the noise power to lower by 24 dB. It's a very useful piece of knowledge, okay? 6 dB per bit improvement. When we talk about quantization, there's a 60 dB per bit improvement. So the idea is that you can afford the recommendation. We recommend that when you can afford, the more the merrier. You want to quantize your signal with more number of bits as much as possible. As much as possible. If you can afford 24, don't satisfy yourself with 16. Ask for 24. Okay? That's exactly what's happening in the audio industry. A 24-bit sound card, so much better than 16 bits. People claim you cannot be satisfied with CD quality. CD music is only 16 bits. It sucks, right? So these are valid discussion because 6 dB, when you increase the quantization, the string by one more bit, you suppress the noise power by 6 dB. Okay, so this figure I like it a lot. It tells us a lot of things. All right. So any comment? That's all I want to talk about quantization. It's very practical. So this last slide I just sort of skip. So this is again to remind us that the entire chain of sampling starts from the continuous time. You want to exclude aliasing first, prevent this from happening in the analog domain, and then we can use sample and hold and convert our time domain signal with the sampling period to the discrete time domain. And then in the middle, that's what we will talk a lot about for the rest of this semester. DSP all happens inside here. Okay. So when we finish processing our signal, then just use a DA converter to go back to the continuous time domain, and there will be some compensation reconstruction filter that can use to ensure that this equation approximately holds. Okay, let me explain. This equation, how do we read it? So everything here happens in the big omega, okay? Big omega. But the relation between big omega and small omega, we have this relation that I introduced to you a few weeks ago. Big omega has a unit, for example, radian per second, but small omega has the unit is radian per sample, right? So there's this equality that's useful. But otherwise, to read here, H0 means the frequency response corresponding to sample and hold. Okay, that's H0, sample and hold. And here, that's okay. It actually goes from this side, yeah. But here, AA stands for anti-aliasing. Okay, anti-aliasing filter might not be ideal, because it's analog circuit design, right? May not be ideal. And sample and hold, this is for sure, it has a closed form expression. Reconstruction filter might not be ideal, okay? Such kind of things are discussed in the textbook, but what's important here is this relation right here. In this product of 4 terms, only this term is in the small omega domain. So this is DSP, okay? DSP happens in the middle. and its effect is going to be, most of the time we talk about filter design, okay? We design a filter in the small omega domain so that it's low pass, high pass, it's differentiator, so everything happens in the digital domain. But otherwise, when we multiply all four of them and assume that if the three of them are ideal, then the effective 等效的, the effective system in the, if you talk about the entire chain, the input is in continuous time, the output is also in continuous time. This is an analog system. You can think of it as a black box. As a black box. Input, output, all analog, so yeah, it's an analog system. Without knowing that in the middle is actually digital. Right? So that's kind of the overall thought of how we process analog signal in the digital domain. Okay, and ideally, hopefully, if the three of them are ideal enough, then your effective system as a function of omega, that analog filter will correlate to your digital filter response in a simple manner. Okay, just constant. They are just proportional. Yeah, with this rescaling of our frequency variable. This is the scaling of the frequency variable. Okay. Yeah, so that's about all I want to talk about analog digital conversion. And let's probably take a break. Let's take a break. And when we come back, let's briefly look at home.